going to try and make anaerobic digestion not boring like Kritik was saying it is. But I want to start with just a few numbers here, because we hear a lot that there's energy in fecal sludge. And I want to put that in perspective. If we think about the average person producing 400 grams of wet feces and 1 liter of urine per day, what sort of energy are we talking about? And you can see here various numbers. I don't want to go into too much detail. But the bottom line is that it is energy, but it is diluted in a lot of water. And it takes an awful lot of energy to vaporize water. And when we think about drying fecal sludge, that's a very big energy-intensive process. And when we do anaerobic digestion, we have the potential to recover a fair amount of energy. And the mouse is starting to disappear, so. Okay, when we do anaerobic digestion, we have the potential to recover a fair amount of this energy in the form of biogas that we can burn for beneficial use. And our plug here is to use that energy to heat the effluent of the digester, to heat sterilized things. And as I showed here in the previous slide, heating is not a very energy intensive process. So we need only a little bit of energy to heat. So this is our process here. This is our idea. If you think about collecting human waste as it would go into a pit latrine and putting it undiluted into a digester, conduct anaerobic digestion, and recover the gas, and then burn the gas into a very effective heater that is located on the far right. And combine this heater with a heat exchanger. It would recover some of the heat, so we can preheat the digester effluent and therefore decrease the energy demand of our heat sterilization. And if you do the balance, it's very feasible. You could use a fraction of the biogas that you're producing to do that. And so therefore my talk is going to be separated into two parts. One part where I'm going to be talking about the anaerobic digestion of concentrated waste, and another part where I'll talk about the heat exchanger system. The first thing we said to do was to work in the lab with a simulant fecal sludge. For that, we looked at various recipes that we adapted. In a nutshell, we're mixing yeast and polyethylene glycol, various material miso, to form artificial poop. And it's always a big kick with the students. What's very important to have is not so much the rheological properties, but really have the right BOD, the right biodegradable matter in that synthetic feces, and the right nutrient and nitrogen content in particular. And we're using some of the average values published by the World Health Organization as our target, about 400 grams of waste feces per day, 1 liter of urine. A lot of numbers here, but we don't want to go into too much details. The bottom line is that we are matching the real thing with our recipe. It's a lot easier to work with stimulants in the lab. And we're right on in terms of the COD, the BOD, the biodegradable, the suspended, and the nitrogen as well. Of course, there's a lot of variation in nitrogen content in urine. We have to settle on a value. This is a biogas potential test similar to what was shown by the previous speaker, where we put in a flask, a closed flask, our feedstock. We put an inoculum and we monitor pressure over, here you see the course of 20 days, and we convert that to how much biogas is produced. And what you can see is one of those traditional standard curve. We can produce roughly 400 normal liters, NLs for normal standard condition, per kilogram of COD. And you can see some slight difference between feces alone and feces with urine. And that's something I'll come back the effect of urine, in particular, the effect of nitrogen. Those are good values. Those are values that are normally obtained by sewage treatment plants. So we conclude from that our simulant is a good surrogate for working in the lab. We can take the slope of this curve and derive a rate that's useful for reactor design. But we really want to do that in a digester. Sorry. And this is the digester we built. We decided that it would be, that all our calculations would be done on a 10-person household basis. We scaled it down by a factor of 33, so this reactor is effectively a third of a person. In the lab is 17 liters. The hydraulic retention time in the system is 40 days, which is pretty standard. And the experts will recognize some of the numbers here. We're operating at 30 degrees centigrade. So in essence, this reactor is fed once a day with 300 milliliters of synthetic urine and 100 grams of wet feces. I want to stress here that it's not being mixed, and it's fed intermittently. And you can see the location of the feed and the overflow. It's a floating dome digester. Here's another picture. You can see the tube where we're feeding it. This is before it's being filled. You can also see we have an aquarium heater here, and you can see the overflow. And that's a picture of the surface of the sludge. You can see some scum. You can observe some little bubbles of biogas pumping the surface. That's during operation 2 on the right-hand side is the overflow. We're not producing drinking water. This is the effluent liquid. You can see it's pretty turbid. And I'll give you some numbers in terms of COD and what it contains as well. This is right at the exit of the digester. So here's the startup of our system, and what you can see reported as a function of the operating time is the biogas production in terms of liters of biogas per grams of COD. Our biogas contains about 65% of methane. You can see also we ramped up the system. We didn't just start dumping the full amount, but we ramped it up slowly. We wanted to give the chance for the bacteria to adapt to the concentrated waste. And we also ramped up the nitrogen contents, because as we heard earlier, ammonia is inhibitory to anaerobic digestion, and we wanted to give the chance to our bacteria in the system to adapt to the nitrogen concentration. And if we, this is where I wish I had a pointer, but at day 100, we increase the concentration of urine to the full strength. And it's going to be really tough. I think I'm going to just, thanks for trying. Thanks. So at day 100, we increase the nitrogen loading to the full strength of urine. At that time, we had reached a steady state where we were producing about 400 liters, the equivalent of 400 liters per day for a household of 10 people. You can see the numbers at the bottom. After we increased the nitrogen loading to the full strength, we saw a decrease in the biogas production, which indicates that there was some effect of the increased nitrogen in our system. But overall, we were pretty happy with those results because they indicated that we would produce about 350 to 400 liters of biogas per day for a 10-person household. And again, those numbers are in the range of what you obtain in modern digesters. They may be 10-20% lower, but they are within that range. And again, they're done with a digester that is not mixed and that is receiving concentrated waste. This is a bit of a busy slide, but we're following here the total COD on the left and what the influence is, and you can see how it ramped up, and what the effluent is. And you can see that around day 120, when we increased the concentration of nitrogen in influent, we can see some effect the system is kind of slow to react. Remember that the HRT is about 40 days. And we typically see on the suspended COD a very good removal of the COD. The dissolved COD, there's some residual there, mainly in the form of acetate. And you can see that it's kind of creeping up towards the end of this experiment. This is ongoing, and we'll of course observe and see what happens. Those results as of last week. So if I summarize the effect of nitrogen, what we've seen so far, we see that up to day 100, we had what I call the better working conditions, where the nitrogen in influence was below 3.5 grams per liter. The free ammonia remained low, the pH was very stable, the system was operating very efficiently, and we can get something like 400 milliliters of biogas per grams of COD. It's a very good number, a very stable operation. At the higher nitrogen concentration, we see things happening. And again, this is ongoing, so those numbers may not necessarily be steady state, but we see something like 25 or 30% inhibition of methanogenesis. Mainly, we think, because of the increased acetate concentration and increased free ammonia that results from those conditions, which is above 100 milligrams per liter. Again, methanogenesis is a complex process with a number of different bacteria doing different transformation. Those methanogens here are affected, as indicated by increased acetate concentration. We also see some other interesting thing happening at the same time. Remember that we had quite a bit of scum at the surface of the reactor. Now the scum has disappeared. Is it linked to those phenomena happening in the reactor? We don't know. That's something that we are following. We are investigating, of course, the effect of nitrogen in our system, and we're doing here a series of biogas potential tests at different nitrogen concentrations. And those black lines are the trend lines, the slope from which we can derive some rates. And if we plot those rates as a function of the nitrogen concentration, we see a trend here. We want to increase, we want to reduce and test at higher concentrations and continue some testing with the digester to solidify those numbers. We're also interested in the effect of acclimation of bacteria to higher concentration of nitrogen. So that's ongoing. I'm going to switch gears here and talk about our heat sterilization system. And in this schematic, you see what it comprises. Essentially, a heat exchanger to your left and a heater to your right. It's a countercurrent heat exchanger, something very common in the chemical industry, except that this heat exchanger here is designed and works with intermittent loads. It works with very low flow. So we've designed our system to treat with a full scale. So this is being done in full scale in the lab to treat about 14 liters a day. This will be again for a household of 10 people. And we're feeding it a load of 0.6 liter each hour, and we feed that in 5 minutes. We optimize the system for heat efficiency, but we also want to make this so that it can be built with very simple equipment, no moving parts that it wouldn't plug, and that it can burn biogas efficiently. So this is what it looks like. To your left is the heat exchanger. Currently it's a plate heat exchanger, and to your right is the heater. There's some temperature data loggers around. Again, it's being fed from the left. It goes into the heater, and it returns in its own gravity feed, which returns from right to left. This is what it looks like very quickly. It's built with very simple materials. 2 paint cans welded together, a tomato soup can, a bit of tubing. The bottom left the bottom right, you can see a Bunsen burner. The flame fits into the housing of the can. That's a small, scaled down version of your gas heater that you have in your house, essentially. The only difference is that you see those copper pipes that is the exhaust. They're usually coiled inside the system. We didn't coil them here. so we have room for improvements. Here's just the result of one experiment. We're feeding it again, 600 milliliters per hour in 5 minutes. And you can see the legends. Essentially, what it shows is that we're able to heat. You see all those transients because the system is working alternatively. And what it shows is that we can heat the influent by 14 degrees. It may not seem a lot, but that's about a third of the power that we need to heat the effluent from the digester. And that's a significant heat recovery. And the temperature that would then enter the heater are the temperatures that are circled in red. We tested the thermal efficiency of our version 1 heater as a function of temperature. And here the efficiency is essentially how much methane we burn. I'm sorry, the heat we gained divided by how much methane we burn with the proper units. And what you can see is that at lower temperature, of course, is more efficient, and it decreases with the increase of temperature. The red line here is what is in the US rated Energy Star. And for that, you can have government subsidies for your appliances. So we're doing pretty good here for a version 1 prototype. And as I said earlier, there's room for improvements. So we're pretty happy with this design. And again, it's not being mixed. There's no moving part. It's built with all very simple equipment. This is the heater performance in the more transient mode when we feed first pure methane at different flows, and you can see the time it takes for the heater to regain temperature 75 degrees with different operating modes. And last mode circled to your right is when we're using biogas that we produce in our digester. Doing a few calculations, we see that again for a household of 20 persons, this heater would need about 230 to 280 liters of biogas per day to keep a temperature at 75 degrees. And that's about 65% to 75% of the biogas that we produce, we would produce in our digester. So what we see is that we're able to produce sufficient gas to maintain the right temperature in our heat recovery system. We then moved on to do some heat sterilization testing. Our approach has been the following. In the lab, it's a lot easier to work with E. coli. There's very quick growth and easy to quantify. So when we're feeding E. coli suspension, again, intermittently in a kind of simulated field condition in our 0.6 loads. And we're measuring the E. coli at different points in our system. From that, we can calibrate and we validate a mathematical model that we have that accurately describes the dynamics of flow, of heat, as well as heat deactivation of our pathogen. And then we can simulate the performance for other pathogen of interest, in particular helminth and virus. And I work with those before we have the heat deactivation constant. So in pictures here you see what it looks on plates. These are some numbers, some bacterial counts from E. coli in the inlet before the heater, so that's after it has passed the heat exchanger for 3 different scenarios in terms of temperature in the heater. And you can see that at the highest temperature, we do get a significant deactivation in the heat exchanger already. When the heat is at 75 degrees, we don't detect any pathogen after the heater or after the effluent. The cumulative sample is that we put all the effluent in one bucket and we make a measurement from there. And even at 55 degrees, we get 4-log reduction in the system. So I'll just come to my conclusion slide here. In summary, what we've shown is we can effectively conduct anaerobic digestion with concentrated waste undiluted human waste, we're getting some pretty decent biogas yields. There's an issue with ammonia that we have to deal with, and depending on our current result, future ongoing work, we may think about some things like urine diversion to diminish the ammonia load. We've designed and tested a heat recovery system, and it's working pretty well. It's pretty efficient, and we are able to accomplish pretty good deactivation of our indicator organism, and we're able to model the flow. We also are able to show that there is enough biogas produced to heat, sterilize the effluent of such digesters. And that, I think, opens some possibilities to provide decentralized sanitation that would not release pathogen. The system is very simple, there's no moving parts. And then coming to my title, if we think that organic matter left unattended will release methane, our system would reduce the footprint by about 7 tons of CO2 equivalent per system per year. What are we, just one more slide, we're working on, we're building a new heat exchanger, a tube and shell that will be more efficient. We're also value engineering our system, thinking about passive solar to augment the amount of heat, or simple thermostats to regulate temperature and save on biogas. And then we are looking forward to moving into a demonstration. We have a lot of contact with different communities in Peru or in Africa. And also working, for instance, running out of time, so with students, a team of students who build a cogen system that will take the biogas and produce electricity in heat. And I want to acknowledge the funding of the Bill and Melinda Gates Foundation and my contact information, and hopefully this time for a couple of questions. Thank you.